for coming. You'll see a lot of affiliations on there, partly because I started with the Stardust project last month, so I don't have any pretty results to show. But this work was essentially done or initiated while I was still a PhD student at KU, but also was working at Los Alamos. We just finished turning in the revision for this paper this Monday, so hopefully this should be published pretty soon. Response surface, if you will, you can think of it as a fancy interpolation technique. It was developed by a senior statistician, David Higdon, at Los Alamos. And so we applied that methodology to modeling satellite drag coefficients for spacecraft with complex geometries. So the outline for the talk today is essentially the beginning with the motivation for the work, giving brief introduction of where the work is leading us, describing the response surface methodology, some nice results, and then conclusions. So the motivation, I mean, everybody here in this room should pretty much know why we are here, but part of it is dealing with space debris. There are two ways we can deal with space debris. One is ADR, active debris removal or mitigation. The other one is collision avoidance. So this work deals with the collision avoidance aspect of it. As we know, recently, or not recently, 2012, the National Research Council published a report which cites atmospheric drag to be the largest source of uncertainty in the low Earth orbit regime, and specifically cites inaccurate density moles and inaccurate drag coefficient moles as a cause of this uncertainty. When we look at the drag coefficient or drag model, drag coefficient imparts direct uncertainty onto predicting the force due to drag, and also indirectly into atmospheric density modeling, because typically atmospheric models are derived using a constant value of drag coefficient for objects when you are inferring densities using drag data. So, brief introduction to the physical drag coefficients. The idea here is to move away from fitted or fixed drag coefficients and move towards physical drag coefficients, which we believe captures the true or physical nature of the interaction between the atmosphere and the space object more accurately. So, the drag coefficient in LEO depends and is a strong function of gas-surface interaction. I'll quickly explain what that is. Atmospheric composition and temperature, surface material properties and the surface temperature, relative velocity between the spacecraft and the atmosphere, and the spacecraft geometry and attitude. Because most of these simulations or most of the satellites or objects we deal with in this work orbit over 200 kilometers, we are dealing with free molecular flow where the interaction between the atmosphere and the surface is dominated by gas-surface interaction. There have been various different gas-surface interaction models proposed and used in the past. On the top left, we have a specular reflection coming in, going out at the same angle. On the right, top right, we have the diffuse model. And at the bottom, if you see, maybe you guys can see this one, but on the bottom, we have the quasi-specular model. So it's a diffuse lobe around the specular direction. In this work, we use the quasi-specular model, which was developed by Cecchiniani. So we use the CLL Cecchiniani-Lampus dot model. And because even in free molecular flow, closed form solutions do not exist for concave or complex geometries, we need to implement numerical modeling and then use some sort of mathematical fitting, in this case response surface, to predict our drag coefficients. So just a quick methodology cartoon. Essentially, the idea is to use a data set which can be attained using either experiments or simulations. In this case, we are using simulations. Doing experiments for drag and atmosphere will be very expensive. So we are using, in this case, test particle Monte Carlo method. Test particle instead of DSMC because we are in the free molecular range. We are not dealing with intermolecular collisions. TPMC is just as accurate while much less expensive, computationally less expensive. Then we need a mathematical model where we can use this data set to interpolate for unobserved phases. So there we use the responsiveness formulation, and when you use a mathematical model, you will typically have coefficients. For example, if you're doing a polynomial fit, you would have to predict or you would have to estimate the coefficients. In this case, we estimate the coefficients, in other words, covariance and other parameters using Bayesian approach and a Monte Carlo MCMC approach. And then we'll see the prediction formulation. So the spacecrafts that we dealt with in this case, we want to diversify the set of spacecraft that we use. On the top left, it is not so simple but not so complex geometry either. It's the gray satellite. On the top right is the simplified model of the Hubble Space Telescope. We use that because we deal with the articulating satellites, or articulating solar panels. We wanted to see if we can apply the technique to satellites with articulating solar panels. And the bottom is, as we all know, the ISS with a highly complex model. So, because we wanted to cover the entire parameter space, and we wanted to avoid outliers or avoid extrapolation, we used the Latin hypercube sampling just to make sure we have uniform sampling in each parameter space and over the entire range of the parameter space. And we developed the model developed a response surface model for each individual species. And what I mean by each individual species is in the atmosphere, depending on the altitude, you can have anywhere between 2 to 8 different individual chemical species. For the altitudes we're dealing with, we use 6. The other 2 are usually negligible. But we developed a response surface model for each species, and then we calculate the overall CD using this relationship. The nominal, the parameter range that we used for each individual parameter is shown there. What is not shown is that for each of the satellites, we also need to include the attitude angle, which is the pitch and yaw, as well as for the Hubble Space Telescope, we need to also include the attitude for the solar panel angle. So that's not included there, but it covers again the entire parameter space. And okay. So, and one of the reasons why we selected the response surface methodology, because it is insensitive to the number of dimensions you have in your model. So you can include as many independent parameters while you can still evaluate the model in a fraction of a second. It is not impacted by the curse of dimensionality as in terms of lookup table or something. Right. So let's go to formulation real quick. We use the Gaussian formulation. If X is a cumulative sample of input parameter space, so essentially we have a set of input parameters where we have a number of samples of the input parameter space, and Y is the associated output to those inputs. Right? So we assume that the outputs have a Gaussian distribution. It's a multivariate Gaussian, uncorrelated in each dimension. So it's independent in each dimension, and we standardize it to have a zero mean. And we have 2 contributions for covariance or uncertainties, if you will. One from the distribution itself. The other one, because we are using test particle Monte Carlo, the simulation code has sort of noise associated with it. So this is essentially uncorrelated Gaussian noise, if you will. On the right is our spatial correlation matrix. So as you move 2 different observations that you made closer, the distance between the 2 goes to 0 and R goes to 1. So essentially you're saying you're predicting your observed state. So that is defined by the spatial correlation matrix. So in the previous formulation that I showed, we have in total, P plus 2, like it says, because we want to estimate theta for each dimension, for each direction, for each parameter, and then the two covariance parameters, lambdas. That we do using a Bayesian approach. So we give theta lambdas gamma priors, and we give thetas beta priors, and then we use the data set that we have collected to come up with a posterior distribution for the parameters. Now, since this posterior distribution is complex and does not have a closed form, we need to estimate the parameters using Markov chain Monte Carlo. So you can do it two different ways. Either you can do a mean of a large sample and use that as point estimators, or you can use the sample and produce equivalent number of outputs and then use the outputs for the conditional distribution, which we'll see in the next slides. So once we come up with the model and the estimation, we move on to the prediction part of it. And this is something I just wanted to show real simple with a cartoon. So I essentially, if you have a Gaussian process model, if you randomly draw from it, you're not going to have any sort of, well, you're going to have a distribution to it, but you will not be able to predict the unobserved part of your parameter space very well. So if you condition your draws to observations that you have, then you will be able to predict the unobserved part of your parameter space very accurately. So, and that is what we are doing with the conditional joint distribution. So if you consider a joint distribution derived from yi and xi. Xi is the input parameter space of the initial test data set that we have, and the yi is the associated output parameters. So we know those. Xi is your new input parameters, set of new input parameters, and yi is what we are trying to observe for us to predict. And so essentially, it boils down to a simple Gaussian where you can predict your unobserved condition on your observed, or your it's not a test data set, but on a condition on your original data set, and it's essentially a Gaussian distribution. Right? So that's what we saw in the last slide. So moving on to results, we did this, like I said, for 3 different satellites. For GRACE, like I said, we did it for individual species. We did models for individual species. And so on the right, what we have, so what we did is, in addition to the training data set where we generated an additional test data set where we compared estimates from our responsive model to the test data set and calculated the residuals to see how well we are doing. And on the right is essentially showing you the comparison between the test data set and the test set predictions, which is essentially the predictions for the responsiveness model. On the bottom right, we have the residuals, and I don't want to say it has a Gaussian nature to it, but it doesn't exhibit any undesired trends. That's what we are really going after. And on the bottom left, we also did a test set with multiple species just to see if we combine individual species, how do all the individual models perform compared to when we do a multi-species model. And we were very happy. And when we started the work, we set out a target for keeping the errors within 1%. And as you can see, we are well within 1%. For the model in pure atomic oxygen, we had a root mean square percentage error of about 0.705. And that is, and for the multi-species, we ended up with 0.686 because some of the errors might be canceling out when you take into account all the different species together. For the Hubble space, we were, okay, we again repeated the same process. In this case, we used a 1,000 member test data set. On the other two, we used a 100-member test data set just to see, can we improve the prediction if we have a larger test data. And in this case, we did see improvements in the error. If you have a larger data set, you have better predictions. and your residuals will typically, again, the distribution is Gaussian, but again, the distribution we don't know necessarily may not be, we know may not be Gaussian, but it doesn't exhibit any undesired trends. For the International Space Station, this is where we managed to reach an error of about 1%, but part of that can be attributed to the fact that ISS is a lot more complex shape, and also in the case of ISS, we only used a training data set sample of only 400 members, whereas for the other two, we used a training data set with 1,000 members. So we wanted to see if the model has any sensitivity to amount of test data or the training data sets that you use. And we found that it does have a slight sensitivity, but even with a small data set, training data set, we were able to maintain the errors very low. So real case results, what we did is we took GRACE, because that's the satellite we have precision orbit ephemerides data essentially derived from GPS. We have that data. So we wanted to see if you propagate using an initial condition for a given day, using all the different drag coefficient models that exist for the satellite, how do we compare to all the other models that currently exist? So, for example, on the black, we have drag coefficients for the response surface model. The dotted blue, or if it is blue, is drag coefficients from Sutton at Air Force Research Lab. And then the faint constant red line is from Bowman from the Air Force Space Command, where they use a constant drag coefficient. At the bottom, we see position errors as a function of time when you propagate this orbit and compare and calculate the errors with respect to the precision orbit ephemerides. And we see that after after about 60 hours, the RSM model starts to outperform all the other models. And for the case of constant drag coefficient, the errors go exponentially almost. And so we are very pleased with the fact that our model outperformed all the other models in the position error sense. So to conclude the talk, we were successfully able to implement the response surface methodology to modeling satellite drag coefficients. We developed models for different objects varying from low complex surface geometry to highly complex surface geometry, also including articulated solar panels. And we did very well with the worst case error coming in case of ISS at about 1%. And in terms of GRACE, we managed to outperform all other existing models in terms of position errors. That concludes my talk. And at this point, I'll be willing to take any questions. Thank you.